Rocky. Shh.
Hi everyone, so today we will be talking about areas of composite shapes. And if you would be looking at our learning intention here, it says that we want to know about shapes, we want to calculate area of composite shapes, and hopefully we'll be able to understand how area formulas are applied today. Okay, so what I want to accomplish for today's lesson are two questions. Okay, so the first question that we want would be, what area of formulas do we know and how were they developed? And then the other question that we want to figure out today is that what are composite shapes and what strategies can we use to calculate the area of those shapes? And I want us to emphasize on the term strategies. So we'll be starting off with the first question that we want to answer today, which is, what are the formulas, or what area of formulas do we know and how are they developed? So when we say developed, how do the mathematicians tell us or say that this is the formula for figuring out the area of this kind of shape? What is area? What are we actually calculating when we're learning about area of shapes? And most of the time I get the answer, it's the inside of the shape, miss. But what's inside? What's the inside of the shape? Okay, what specifically are you talking about? Is this the inside of the shape? And what about it? What are you actually measuring in that inside of the shape? We could probably look at first the basic shapes, and it's a square because the lengths would be equal, right? So looking at these shapes here, maybe how they were drawn would give you a clue. So when we're talking about area, what are we actually calculating? This one here would have a length of 2, and that one there would have a length of 2. And you'd probably say, miss, you just multiply them. It's 2 times 2, and therefore the area of this shape is 4. But who told you that it's 2 times 2, and why is it 2 times 2? Well, because when you say area, it's the inside of the shape, but what's specifically in the inside of the shape that you're actually measuring? Or maybe what are we counting when we're talking about the area of shapes? We're counting the number of unit squares that make up that shape. Okay, and if you notice here, you've got 1, 2, 3, 4 unit shapes that make up that square. Okay, and if you do that for a rectangle, you could probably say this one has 6, because then that's 1, 2, 3, 4, 5, 6. Yeah, so where's that times or multiplication coming from when we talk about area? Well, we could say that has 2 squares, lots of 2 rows, or you could probably say it's 2 lots of 2 columns, right? And you could also say this one here would be 3 times by 2, because each row here would have 3 squares. And how many rows do we have? There are 2 rows. Yeah. Now, when you look at the triangle here, would you be able to count the squares? Well, you can certainly say that's 1, 2, 3, right? And if you do some problem solving strategies here, you could probably say, I could get this triangle here and move that over here so that it will complete that square. So now I'd say there's 1, 2, 3, 4 squares, but then there's a half here that I wouldn't be able to get a partner. So that similar to what I did here, I could just simply put that other shape there and get rid of that one, of the top one there. Okay, let me put that and we can get rid of that. that make sense? Yeah. So then I would say that this one here would have how many unit squares? There's 4.5, right? Now you could probably say, well, we said we had 2 questions that we want to answer, and part of the second question is what strategy, right? So that's one strategy there. We could also, or someone could also argue that, say, maybe what you could do is to come up with and complete that rectangle there, right? And complete all those divisions there to say, indeed, there's 1, 2, 3, 4, 5, 6, 7, 8, and 9 squares, but it's not the whole rectangle that, or in this case, it's not the whole square that we're after, but instead we're just after half of it. And therefore, you can say that a triangle would be, imagine it as if it's a rectangle or a square, but you just need to half it, okay? And that's why when you calculate the area of a square, you could probably say it's length times width, but then the length would be equal to the width. You could say it's the side times the side, which is, you could write as side squared, right? The same thing with the area of a rectangle. That would just be length times width, or the base times the height, right? Base, breadth should be just the same, and therefore we've got base times the height, yeah? And that's why for the triangle, you would have half times the base times the height, okay? So now we've established these formulas here. So that's area for the triangle, area for any rectangle, an area for a square, okay? So without having all those divisions for us to be able to count the number of unit squares inside the shape, we would be able to simply use those formulas, okay? So how do we figure out the area of this trapezium? So firstly, what we can do, because what we know would be the area of squares, rectangles, and triangles, I can draw up a diagonal here and say I can cut up this trapezium into 2 triangles. Let me name the bottom as A1 or area 1 and the top one area 2, okay? So now I'd be able to figure out what the area of the bottom bit or the bottom triangle. We say the area of a triangle is half times base times height. If I name the base as B and the perpendicular height, when I say perpendicular height, it makes a 90-degree with a base, right? It makes a 90-degree angle with a base. So then I've got 1/2 times base times the base times the height, yeah? Now, it's not only that triangle on the bottom, but also I want to figure out or add the triangle at the top, okay? So then I'm working now with this triangle here at the top, but it's also a triangle and therefore it's half times base times height. But I can't really just say that this is B, because looking at the lengths of those, this length here doesn't look like it's equal or have the same length as that one. And I can't simply assume that, right? So then I would say, let me give this a name instead of B, give it a name as A, right? So I've got the base is A. If you invert that triangle at the top, that's your base. Why do I want that as the base? Because I would be able to figure out or say that this is the height or the length that's perpendicular to the base, right? It makes a 90-degree angle with the base, right? And name that as the height, which is the height I have here. In this case, you have the height here equal to that, and we don't need to give the other height on the left a different name, right? Because they are just equal. And therefore, we could say what? That's half times A times H. And because of algebra, we could say I can factor out the half times H because they are your highest common factor. And that's half times H multiplied to B plus A, right? Or that, just to make it a little bit prettier, I could say B plus A is the same as A plus B. And I could say that's really just half times A plus B, rather, times H. And that is now our area formula for a trapezium. Now, what do we call this shape? We call this the rhombus. And when we have a rhombus, we can do the same as previously and with a trapezium, and we can divide them into two triangles. In this case, because this is a rhombus, we would say that, and we know the properties of rhombus, that it would have an axis of symmetry. The diagonal is actually your axis of symmetry there, right? So that the area here would just be the same as the area there, right? Okay, so let's probably figure out first what would be the area of the top, and we can just double it later, right? So we could probably say the length of our diagonal here is x units. Okay, let me just write it here because I will need to write something inside. Okay, so we know those are our areas. We can get rid of those because I need to draw another diagonal from there to there. Okay, and I know that those diagonals bisect each other. When I say bisect each other, they cut each other into two equal parts. X is actually my base. And then if I would say that this whole length here is y, I could say that the height here would be half of y, right? So let me write that down. The area would be half. What was our base? That was x. And what was our height? That was half times y, right? And we said since the top triangle is equal to the bottom triangle, then we just need to double that, yeah? And what would that be equal to? We would have what? We can say numbers first, then letters. And what's 2 times a half? That's just 1. 1 times a half, you get 1/2. And then you have x times y, or simply xy. And what are the xy's? The x and y are the diagonals. Okay, right. How about this one here? That is we call that a kite, right? What are the properties of kites? We know that the adjacent sides are equal, right? What else do we know? That their diagonals form right angles, yeah? And what else? You could probably have a look at the one we did a while ago with rhombus, and we can find two triangles of equal areas, and we thought that was an efficient way to figure out the area of the rhombus. So the same thing with kites. We do have triangles here, right? And we could probably say I can cut that triangle into that kite into 2 triangles, the one on top and the one on the bottom, but they aren't equal triangles. So it might be a little bit trickier if we cut them into those 2 triangles. So we could probably say, well, I can cut that instead vertically, and I would have this as equal to that. I could name or have this length as x, right? And that would be our base. Then I would have the height to be what? This height here, which is perpendicular to the base, right? And I would say this here would be y. Then I could say it's really just half of y. And I can write a is equal to half times the base, which is x, times the height, which is half times y. And since the left triangle is equal to the right triangle, then I would say I can just double that, and very, very similar, right? With our rhombus area of a rhombus formula, that would just be half times xy. And again, x and y are the diagonals. Well, the last one there would be your circle. And we divide them into our sectors, right? And then put them together, such as this one here, right? And we notice it's like a rectangle. And we know the area for a rectangle is base times the height would be the radius. That one there would be the same as this one here. So it's base times height. And we know that the height would be equal to the radius. How about the base? What would be this length here? Well, if you would be looking at our drawing here, this one here and the one here on the side would actually be the length around that circle. And we know that length around the circle to be the circumference, right? And we know the circumference to be equal to 2 pi r, right? But when we multiply base and the height, we just want to multiply it by this, which is really half of the circumference, right? So if we write that down, that's 1/2 of the circumference times by the r, which is the radius. And if we replace C, the circumference, with our formula, 2 times pi times r, then, and we further simplify that, we could say half times 2 would be simply 1. So we can cancel them out. And looking at this one, we have pi times r squared. And therefore, our area formula for our circle is pi times r squared. To summarize, these are our area formulas, okay? We've got the square, we've got the rectangle, the triangle, the rhombus, or that would just be the same for parallelograms. We've got the trapezium and also the kite, and also for the circle. For maybe the next lesson, this is what we will be focusing on, which would be sectors or simply a fraction of your circle. Okay, so I think we've answered the first question. Our first goal is, what are the area formulas that we know and how are they developed, right? And so we move on to our next question. What are composite shapes, firstly? And what strategies can we use to calculate the area of those shapes? What is a composite shape? They would be shapes that would be composed of what? Basic shapes or simpler shapes, shapes that we know the area formulas of, or shapes of those area of those shapes that we were able to develop, just like what we did a while ago. So just like this odd looking shape here, it's a composite shape composed of a semicircle, another semicircle, and also a square, right? If we put together these two semicircles, it forms a circle, and therefore we could simply say, let's just calculate the area of that circle and then the area of that square, and therefore we would be able to figure out the area of that. Okay, so it's adding the areas, cutting that shape into simpler shapes so that we would be able to come up with the area. of that composite shape. Okay, now sometimes it's not adding them, but instead looking at it as, is it a shape wherein it's something was taken out of that shape? Just like if your question here is, what would be the area of the shaded region? Okay, you could probably say, well, that's really just a square, right? Just like that one there. And you cut out a semicircle here and cut out another semicircle here. And those two semicircles would form this one whole circle. And that's why we've got this operation here as a minus, right? Instead of just like what we did a while ago, or the example a while ago, it's adding those two area. Okay, so let's probably have a look at an example here, right? So this is a composite shape, and what would it be composed of? What shapes are they composed of? I could see here that there's a square and also a rectangle, just like this one here, right? So I could assign this as area 1 and area 2, and for me to figure out the area of that composite shape, I could say that's just area 1 plus area 2. We learned, or we know that for us to get the area of a square, that's simply 5 times 5, or 5 squared. And then we add 6 times 12. Okay. And what is 5 squared? That's 25. And what 6 times 12? We get what? 12 is 10 and 2. So 6 times 10 is 60. 6 times 2 is 12. And therefore you have 72. And what's 25 plus 72? That would be equal to 97. And that, what would be our unit? It's square meters. Okay. Let's have a look at this other example here. It's a composite shape composed of two simpler shapes. One is a triangle, and the other one is a rectangle here. Yeah. And again, we can assign that as area 1 and this rectangle here as area 2, and figure out what's the area of that composite shape. Area 1 plus area 2. How do we figure out the area of that triangle? We go half times the base. What would be the base? Well, this one here would be 15, and that one there would be 8. And therefore, this bit here, looking at those two horizontal lines, they both make up 15, but the top is 8. So what's 15 minus 8? That should be this, which is 7. And that would be our base, which is 7, times the height, which is 10. And then we add the area of the rectangle, which is 8 times 10. Okay. Now, what's half times 7 times 10? We can say that's half of 10, which is 5. We multiply it to 7, we get 35. And we can do that because of what? We can use our associative law, right? Grouping first half and 10, half times 10 before we multiply it to 7, okay? To help us with our mental calculations. And then we've got 8 times 10, which is 80. And what's 35 plus 80? Well, 80 to reach 100, you have 20. And we have what other left over from 35, we have 15. And therefore we get 115 square centimeters this time. Now, looking at these two shapes, what could be that strategy that we should use? A while ago, we discussed two strategies. One is adding them together, which was very efficient which is what's appropriate to use for these two examples here. But looking at these two examples here, they look like that we're not adding them, but we could probably say we're subtracting this tiny bit of rectangle from this whole rectangle that we have here. So this time we're minusing the area of the whole rectangle, the bigger rectangle. You could even say A of B of sub B, bigger rectangle, minus area of the smaller rectangle, right? And what's the area of the bigger rectangle? It's 12 times 10, right? And what's the area of this small rectangle here? That's 3 times 4. And what's 12 times 10 equal to? It's 120 minus 12. That should be what? 108 square meters. Okay, so the same thing with this one. Looks like it's what? A square, right? But this trapezium here is taken out or taken off from that square. Okay, so then again, our strategy is minusing them. Area of the square minus area of the trapezium. It's the area of the square. It's simply 6 times 6, or even say 6 squared, minus the area of the trapezium we found out a while ago was half times A plus B multiplied by H, right? And so we write and we replace the values here. What would be our A? We could assign that this is our A, which is 3. And we have our base, or the other horizontal line would be, which is this one here, which is the same as that. And therefore that's simply 6. And what is the height of the trapezium? That would be equal to 3, and therefore we times that by 3. Okay, and what do we have here? That 6 times 6 is 36, minus what's 3 plus 6? 3 plus 6 is 9. Half of 9 would be 4.5. 4.5 times 3. You could say 4 times 3 is 12. And then 0.5 times 3, or 3 lots of halves, you get 1.5. And therefore you get 13.5. And what's 36 minus 13.5? I could probably use my calculator because my brain is tired. And you say that's 22.5 square meters. Now, how about this one here? Are we adding them or are we subtracting them with this one? Have a think. What strategy could you probably use here? You could probably say that you would want maybe this semicircle, right, moves to this bit here, right? And then this semicircle moves to that bit there, yeah? And what shape do we actually form? We could say that the shape that we form would be a square. And that's going to be, let me pick that color, right? And it would be an actual square, and therefore easy peasy, our area for that would be 4 squared, which is simply 16. Okay, so sometimes don't get stuck with them telling you add the areas together or you minus the areas together, but sometimes it requires a little bit of thinking, or maybe I could say smart thinking, right? Just moving those little bits of parts to the other so that it forms a simpler shape, shapes that you know the areas of. Or again, the focus here would be the strategy. Okay, how are you going to strategize for you to be able to figure out the area of these shapes. Are you going to add? Are you going to minus? Or are you going to flip or move around some of the little parts so that it becomes those simpler shapes that you've got there? The other thing that you might need when you're talking about areas of shapes could also be that some of the shapes would have different units, and therefore another skill that you might want to build on would be for you to figure out how to convert between units of area. Okay, so I've got there the video for you to learn that. This might probably remind you of how to do that, this diagram here. So maybe just have those ready, right? Just in case some of the questions that you are to answer here would require you to convert between units, okay? You've got there your extension question, right? Feel free to ask questions about the extension question, right? And then for your exit task today, what I want you to do after you answer the questions from this exercise here, you might want to pick an interesting shape, right, that you were able to answer. And what I want you to do would be to answer or figure out the area of that shape in 2 different ways. Okay, whether the other one is easier or the other one would be harder, then show those 2 methods of solving the area of that shape. Okay, I hope that helped you with calculating the area of composite shapes, and I'll see you next lesson. Stay awesome. Bye.
Come on, Rocky, let's go.